All right, this is the last question I'm going to do. This is what I'm going to call a quiz review question. I looked at my Simple Forces quiz and I thought, about it for a while, and I thought, what's a good question that's going to give students an idea about what to expect in terms of the difficulty, in terms of what kind of short answer questions you might see. So there isn't a question exactly like this one, but it's very similar enough in terms of the difficulty, in terms of what you're doing. So here it is. A 75 kilogram sprinter is running a 100-meter competition on a wet day. They know their shoes have a coefficient of friction of 0.3 for whatever reason they know what that is. But they know they have that as their coefficient of friction when the ground is wet. Normally shoes are going to have a coefficient of friction probably closer to 0.5, 0.6, even 0.7. They're fairly grippy. So not when you get down to 0.3, that's when things aren't very grippy anymore. That's when things start to get very slippery. And 0.1, you can imagine that's when you're like walking on ice or something, when it gets down to that level. Anyway, the question says, how fast can the runner accelerate until the point of slipping/sliding? So before we even start answering this problem, let's actually literally write down what we're trying to find. How fast can the runner accelerate? So we are basically trying to find A in this problem. And we can assume that this is the net acceleration because it's the runner who's running. And because they're accelerating, the acceleration is whatever the sum of all the other forces or accelerations that are happening to the runner. Okay, so a good thing to start with here is forces. Just a little recap on forces. Our runner is running, and when you're running, you're putting your foot down and you're pushing off your foot, right? So you might think when you're running you'd be doing kinetic friction because you're moving, but keep in mind your feet, your shoes aren't actually sliding. They're not slipping. They are at rest. Individually, each foot is at rest as you step forward. So you're utilizing the static frictional force when you're running. If you start slipping, that's when things go down into kinetic friction. So we are assuming that we're working with static friction, and I didn't put static in this problem here because I didn't want to confuse you. It is very confusing when you think of a moving object. We've talked about that being kinetic, but again, we are dealing with actually objects that are technically at rest every time that they are on the ground. So static friction is what we're dealing with. And basically the idea here is that if the runner accelerates any faster than this, they are going to exceed that static frictional force, and then they're going to start slipping, and they're not going to be able to push with as much force forward, so they're not going to go as fast forward. And this is a problem that happens all the time. I remember when I was younger, I was in school, I was trying to race a friend with my car, and it was a rainy day. We were at a stoplight. We both accelerate once the stoplight hits green, but because we were trying to accelerate so fast, our cars couldn't grip the road, and we basically could not accelerate forward at all. So this is definitely an important problem that sprinters, runners, have to know about. They don't really need to do math or anything, but it is a thing that affects them. So remember that when you're dealing with force problems, it's always good to draw a free body diagram to start out. And the main idea here is that we have a runner. And I also did this one just to kind of give you an idea about why this is happening. So here's our runner. We have their force of gravity on the ground. We have the normal force, the ground pushing back up on them, which allows them to have a frictional force. And the reason why the runner's moving forward, we're going to assume they're moving to the right, is because they are getting a force to the runner from the ground, right? And this is a little bit of review. I wanted to tackle this. So here's the ground's perspective. The ground does have weight, so there would be some force of gravity, some normal force. I just kind of assumed we don't need to deal with that. But here's the ground. The ground is being pushed backwards by the runner, right? So the force from the runner to the ground from the runner, GR, force to ground from runner, is the opposite as on the runner. So when a runner is going forward, they're receiving a force from the ground, and the ground is receiving a force in the opposite direction from the runner. This is one of Newton's laws. I think it's Newton's first law. Every force has the equal but opposite force, equal opposite reaction type deal, right? What is this force that's causing the runner to get a force forward? It's the friction force, right? If there was no friction at all between the ground and the runner, think ice, that runner would basically just be slipping and sliding. They wouldn't be able to accelerate. So this is our free body diagram we want to focus on. What about net forces? As we said, there's a net acceleration, or that's what we're trying to find. So what's the net force here? I'm just going to draw this as a supplement. Here's our runner, which we'll assume is a box. The normal force and the force of gravity cancel out. So the only remaining force here is the force to the runner from the ground, which is the net force. Right? So that's what we're going to utilize to solve this problem. So now that we've identified that, we're going to write, let me use my pen that I've been using before. The net force is not equal to 0. It's equal to the mass of the runner times their net acceleration. And the only force that is not canceled, that will result in the net force, is the force to the runner from the ground, which is the force of friction. Right? So there is our expression. Here's me identifying, hey, this force from the ground is the result of friction. So let's use what we've been using in the past. The mu times the normal force to represent the force of friction. And just as we realized, the only force that's causing the normal force is the force of gravity. So we can say that the normal force is the force of gravity, which is mass times gravity. And we can substitute that in there and get a new expression. So let's rewrite that expression now. The mass times the net acceleration is equal to the mu times the mass times the gravity. Looky here. We don't even need to know the mass of the runner, because the mass of the runner, the only mass given to us in the problem, cancels out. So in this review problem, and in many problems, you'll see that sometimes you'll be given a mass, but you actually don't need to use it. And you'll realize too later on, you don't need to use this 100 meters thing also. These are sort of supplementary or unnecessary informations that you need. If you did solve for, say, something using the mass, then I guess you could have plugged it. I mean, you could have plugged it in. It's just it would have canceled, right? So anyway, we have our problem set up. We are able to see here, if I just rewrite this, that the net acceleration is simply equal to mu times gravity. And that's what essentially mu is, what the coefficient of friction is. It's telling you the percentage that you can accelerate based off gravity, the normal force. So this 0.3 is saying that you can accelerate with 30% of the acceleration of gravity. Let's just go ahead and solve for that. And we get 2.94 meters per second squared. Okay, sweet. So that is a good representation of sort of the more difficult problems on the simple forces quiz. As you can see, it's not the most challenging problem when you compare it to the other couple of problems I did. You could make this more challenging though, in similar vein to this problem, by adding a kinematics part at the end. You could say, hey, it's a 100-meter race, right? So assuming that he can get up to a maximum velocity of, say, I don't know, 12 meters per second, how fast would it take the runner to finish the race, right? So in this case, what you would do is, knowing their maximum velocity is, what did I say, something like 10 or 12, knowing that the acceleration is this amount, you can solve for the time it takes and the distance it takes to get up to that final velocity. And if that velocity is less than 100 meters, then you would just finish the rest of the problem, the rest of the 100 meters that haven't been done, with that maximum velocity of 12 meters per second. I think that's what I said. And then you can figure out how fast or how long it took the runner to do the problem, to do the race. So that's a cool kind of an extension problem. You can try that out yourself. I'm just going to write this down. How long would it take the runner, the sprinter, to finish this race? It's not really a race, is it? It's such a short amount of distance, but I guess it is a race. So how long would it take the runner to finish the competition, assuming their max speed is 12 meters per second? That's just a challenge. Try it out and let me know what you get for the answer. I don't know the answer off the top of my head, but if you tell me what you got, I can definitely work with you and see if you're able to reach a solution. All right, so that's my review question. Good luck studying, guys.